Lesson 29, Question 1. A card is chosen at random from a standard deck of 52 playing cards. What is the probability that the chosen card is a king or a queen? Okay, my first indicator to me is that they're mutually exclusive is the word or. And then I ask myself, well, can you draw a king and it be a queen in the same draw? The answer is no. So that means that they can't happen at the same time. So they are mutually exclusive. So we're going to have the probability of drawing a king or a queen. It's going to equal the probability of a king plus the probability of the queen. So I'm not going to add their intersection because there's no chance of having the king and a queen at the same time. So that would just there isn't an intersection. So we have the probability of drawing a king. Well, there's 4 cards out of 52 that are a king. And probability of a queen, there's 4 out of 52 again. And this is going to equal 1/13 plus 1/13. And that's going to equal, when you have the same denominator and you're adding, you're going to add the numerator. So 1 plus 1 is 2, so 2/13. So then when we are looking for it, we're looking for addition. The 1/13 plus 1/13 equals 2/13. Great job. All right, moving on. 2 fair 6-sided dice are rolled. What is the probability that the sum of the numbers rolled is either a 7 or an 11? Okay, so my first question when we're dealing with probability is, what is the total number of outcomes that we can have? What's our sample space? So since we're rolling 2 dice, each one has 6 sides, there's 6 options for the first roll, and there's 6 more options for the second roll. So our total sample space, or our total number of outcomes, is going to be 36. Okay, now we're talking about the sum of the numbers rolled is either a 7 or an 11. So how many different ways can I create 7 when I roll a dice? Well, I could roll a 1 and then a 6, or I could roll a 6 and then a 1. I could roll a 2 and a 5, or I could roll a 5 and a 2. I could roll a 3 and a 4, or I could roll a 4 and a 3. And that's as far as we can go to make a 7. And then, so there are a total of 1, 2, 3, 4, 5, 6. So 6 different ways. Of making 7. Alright, so when we look at the number 11, the number 11 is made by rolling a 5 and then a 6, or I could roll a 6 on my first time and then a 5 on the second. So there are 2 different ways here. Okay, so now let's set up our probability statement. Alright, we have a key word here as or, so, and then I ask myself, well, can I have the sum be a 7 and the sum be an 11 at the same time? The answer is no. So we have an or a union is going to equal the individual probability of 7 plus the individual probability of an 11 minus their intersection. So in my head, this is what I see. I see here's all of the ways to make a 7, and here's all of the ways to make an 11. They do not share any of those same ways, so there is no intersection right here. That means that's a 0. So this part is always included in your formula. It's just 0 when there's no intersection, when they're mutually exclusive. So just keep that in mind, that when they gave you the two formulas, one with subtracting the intersection and one without, it really is just subtracting the intersection all the time, but when they're mutually exclusive, they have no intersection, so then it's just subtracting 0. So it is the same formula. Alright, so the probability of the sum being 7, well, there's 6 ways out of 36, plus probability of sum being 11, there's 2 different ways out of 36, and like I said, there's no intersection, so we're subtracting 0. That's going to equal, okay, we have 2 fractions that have the same denominator and they're adding, so that's 8 out of 36 because we added the numerators. Minus 0 doesn't change its value, and 8 out of 36 can reduce down. 4 goes into 8 twice. 4 goes into 36 9 times, so we have 2 ninths. Let's check our answers. Great job. All right. Question 3. A card is chosen at random from a standard deck of 52 playing cards. What is the probability that a chosen card is a jack or an ace? So there's the indicator or, and then double check yourself. Can the card be a jack and an ace at the same time? And that says no. You cannot have a jack and an ace at the same time. So they're mutually exclusive. So again, in your head you have all of the jacks and all of the aces. There's no intersection between these two. They're completely different in the Venn diagram. So the probability of it being a jack or an ace is going to equal the probability of it being a jack plus the probability of it being an ace minus the probability of it being a jack and an ace at the same time, which, because they're mutually exclusive, is 0. They have no intersection. So the probability of pulling a jack, we have 4 chances out of 52. And the probability of pulling an ace is going to be 4 chances out of 52. We're adding and we have the same denominator. So that's going to be 8 because 4 plus 4 is 8 out of 52. And this can be reduced to 2 and 4 because 4 goes into 8 twice and 4 goes into 52 13 times. So we have 2/13. Great job. Okay, which pairs of events are examples of mutually exclusive events? So I ask myself, can they happen at the same time? Okay. Choosing a card from a standard deck of cards that is an ace and a 4. Can those two things happen at the same time? No. You're either an ace or you're a 4. So that event is, those two events are mutually exclusive. Choosing a card from a standard deck of cards that is a heart and an odd number. Can those things happen at the same time? Yes. So this one's not mutually exclusive because they can happen at the same time. Choosing a card from a standard deck of cards that is a king and a heart. Can this happen at the same time? Yes. So they're not mutually exclusive. Choosing a card from a standard deck of cards that is a diamond and a king. Yep. So they're not mutually exclusive. Choosing a card from a standard deck of cards that is a king and a queen. No, you're either a king or you're a queen. So they are mutually exclusive. Let's check our selections. Great job. Alright, so which pair of events are examples of mutually exclusive events? There's more than one correct answer choice. Select all correct answer choices. Rolling a 3 on a 6-sided die and rolling a factor of 12. Are they mutually exclusive? Well, is 3 a factor of 12? Yes. So no, they're not. So this can happen at the same time. So they are not mutually exclusive. Rolling a 2 on a 6-sided die and rolling an even number. Well, since 2 is an even number, they could happen at the same time. So they are not mutually exclusive. Rolling a 3 on a 6-sided die and rolling an even number. Since 3 is an odd and an even, so nope, they couldn't happen at the same time. That means they are mutually exclusive. Rolling a 2 on a 6-sided die and rolling an odd number. Well, 2's even, so they could not happen at the exact same time. So that's mutually exclusive. And rolling a 3 on a 6-sided die and rolling an odd number. Since 3 is an odd number, they can occur at the same time, so they are not mutually exclusive. Great job. Alright, question 6. Anna is choosing a pillow for her bed. The probability that the pillow is encased in microfiber is 0.5. The probability that the pillow is filled with memory foam is 0.7, and the probability that the pillow is filled with memory foam and encased in microfiber is 0.3. Which equation shows the correct use of the addition rule to determine the probability that the pillow is encased in microfiber or filled with memory foam? Alright, so they're using the keyword or there for our, so I'm going to use F for microfiber or M for memory foam. So the probability of being in microfiber or memory foam is going to equal the probability of it being microfiber plus the probability of it being memory foam minus the intersection that it could be both microfiber and memory foam. So in my head, this is what I'm picturing just from the description that they gave us. We have microfiber and all of that is 0.5. So the total in here is 0.5. And then in the other one, it says that this is memory foam. And that total is 0.7. But they also give us a big clue. It says that the filled with memory foam and encased in microfiber, that's this section right here, is 0.3. So that means that the one that's just in microfiber would be a 0.2 because that total circle of being in a microfiber has to be 0.5. So this whole section has to be 0.5. And then being in memory foam, this whole section has to be 0.7. So that means there's 0.4. Since 0.3 of it is in the intersection, there's 0.4 that's out of the intersection. So that has to stay as 0.4 for it to be a total of 0.7. That's how I would visualize the Venn diagram. So that's helpful if you're a visual person. And then they want to know, okay, well, what's the probability of it being So we have our equation set up, probability of it being microfiber. That total is going to be 0.5 plus the probability of it being in just memory foam. The total is going to be 0.7. And the reason why we subtract out one of these intersections, if you noticed, when you count the probability of it being in microfiber, you're including this 0.3 to make it 0.5. And when you count the probability of it being in, in memory foam, and when you count the probability of it being in microfiber, no, timeout. The probability of it being in microfiber is 0.5, so that includes this 0.3 intersection. The probability of it being memory foam is 0.7, and that includes the intersection again. So we're counting that intersection twice, and that's why you subtract it out. So we're going to subtract out 0.3. So 0.5 plus 0.7 minus 0.3 is going to equal 0.9. And we can type that in our calculator. I just glanced at the equations and I saw, hey, I have 0.5 plus 0.7 minus 0.3. That is what I have written, which is correct, and it is going to equal 0.9. So let's check. Great job. Alright, question 7. Julia is in a cereal aisle at the grocery store and is looking at the cereal options. The probability that the cereal is in a bag is 0.8. The probability that the cereal has a prize inside is 0.3. So we have a bag. And the probability that the cereal is in the bag and has a prize is 0.2. So we have a bag. We have the prize. And then being in a bag has a total of 0.8 and then it being in a prize is 0.3, but the intersection is 0.2, so that means that it just being in a bag would be 0.6 without it, because that would give us a total of 0.8, and then the probability of it just being a prize would be 0.1 because we have 0.2 of it in the intersection. So then that's how I would visualize this. And so we have the probability of it being in the bag or has a prize. So that's going to equal the probability of it being in a bag plus the probability of it being in a prize minus the intersection of it being a bag and a prize. Okay, so that's going to equal, well, the total probability of it being a bag is this entire circle, which was 0.8. Notice that it includes that intersection plus the total probability of it being a prize. The total is 0.3 minus the intersection, because that was included twice, so we were going to minus 0.2. And that's going to equal, we're going to come over to our calculator, 0.8 plus 0.3 minus 0.2. It's going to give us 0.9. Okay, so we're going to have 0.9. Great job. All right, now if you're a visual person, like I am, my first question would be like, but you have 0.6 here and 0.1. 0.6 is just the bag, and then 0.1 is just, so 0.6 is just the bag section, and then 0.1 is just the prize section. So how come it's not 0.7? And that's because you were leaving out that intersection completely where it could be a bag or a prize. So if you're looking at this, I'll draw it again. Let me draw that bigger. So we have we have it being in a bag, and we have it being in a prize. So we have 0.6 in here, we have 0.1 in here, and we have 0.2 in here. Okay, well if you look at this, the probability of it just being a bag has to include that intersection as well. But if you were going to just look at the Venn diagram and calculate the probability of it being a bag or a prize, you would do probability of it being a bag is 0.6 plus the probability of it being a bag and a prize, count it once because it's a bag and a prize, is going to be 0.6 plus 0.2 is going to be 0.8. And then we have the probability of it just being in the bag plus 0.1. So that would be 0.9. So again, visually, it's just counting each section individually. The reason why they write it out and we subtract this intersection is because they count it twice when they include the probability of the bag, because it's talking about that whole circle. It's talking about the 0.6 and the 0.2 because that's still selecting a bag, and then the other one, the probability of selecting a prize, is this entire circle, and they include that too again because even though it's a bag and a prize, it's still included in the prize circle. So that's why they have to subtract it out once. Whereas if you're visually looking at it, you have a 0.6 just in the bag, 0.2 of bag and the prize, and a 0.1 of just the prize. So total, either of those is gonna add up to 0.9. So that's just another way to think about it. Moving on to question 8. Drinks are prepared and arranged for a table party. The probability that the drink is grape juice is 0.3. The probability that the drink has a straw is 0.3. The probability that the drink is grape juice and has a straw is 0.1. Use the addition rule to determine the probability that the drink is grape juice or has a straw. So the probability that it's grape juice or has a straw. So just purely algebraically, it's going to be the probability that it's juice plus the probability that it's a straw minus the probability that it's juice and a straw. So that's going to equal 0.3 for the probability of it being a juice plus 0.3 of it being a straw minus the intersection, which is 0.1. So 0.3 plus 0.3 is 0.6 minus 0.1 is going to be 0.5. And then if you like the visual representation, you have to set it up right. So we have the juice and the straw, and we know that there's 0.1 in the intersection, we know our total juice, it has to be 0.3. So that means there's going to be 0.2 in the juice. We know our total straws has to be 0.3. Since there's already 0.1 right here, that means there's going to be 0.2 there. And then if you like the visual representation, okay, so for it being juice, 0.2 plus 0.1 is 0.3 plus 0.2 is 0.5. So either way we do it, it's going to be 0.5. Okay, question 9. I'm going to do the question 9. Here we go. Jonah has 2 large baskets of blocks that need to be organized. There are 50 blocks in each container. Container A has 28 red, 14 yellow, and 8 green blocks. Container B has 28 yellow, 14 green, and 8 red blocks. Jonah bets her sister that if she can choose a green block at random from both containers, Jonah will do all the organizing. Jonah's sister thinks the bet is unfair and would rather bet on Jonah choosing a red block from both containers at random. Which bet has the better chance of occurring? Choosing a green block from each container or choosing a red block from each container? Okay, so probability that you choose from container A a green one, and the probability that from container B you choose a green one. So this one is gonna be not our addition rule, because they're two events. There are two things that are happening to determine one event. So we have the probability that you choose a green from container A. Alright, that's going to be 8 out of 50 times the probability that you choose a green from container B, which is going to be 14 out of 50. So then we're going to have the probability of choosing a red one and the probability of choosing a red one out of B. So we want the probability of choosing a red one out of A is going to be 28, because there's 28 red blocks out of the 50, times the probability of choosing a red block out of B is going to be 8 out of 50 as well. So let's go over to our calculator and find out what those are. So we have parentheses 8 divided by 50 times parentheses 14 divided by 50. That's going to equal 0.0448. This is going to equal 28 divided by 50 parentheses times parentheses 8 divided by 50. It's going to equal, I typed that in wrong, I apologize. It is 28 divided by 50 times 8 divided by 50. So that's going to equal 0.0896. Alright, so now they want to know which bet has a better chance of occurring. Well, is 0.089 greater than 0.044? Yes. So since that's the case, that means choosing a red block is more likely to happen. So choosing a red block from each container has the probability of 0.0896, and choosing a green block from each container has a probability of 0.156. Nope. Choosing a red block from each container has a probability of 0.0896. Yes. And choosing a green block from each container has a probability of 0.0448. So choosing 2 red blocks is more likely. Yes, that is correct. Okay. Great job. So question 10. And the reason why we multiplied on this one instead of added is because they wanted to choose a green and a green from each container. It wasn't an or option. They were 2 individual events. So choosing the green blocks was one individual event, and choosing the red blocks was an individual event. So that's, and then to choose a green block from each one, you had to choose a green block from the first one, and you had to choose a green block from the second one. So that's why I used multiplication instead of addition to find those individual probabilities. Alright, so question 10. Ella wants to use her tablet for 10 minutes to play a game. Her mother says that she can use her tablet for n minutes, where n is determined by either rolling 2 fair 6-sided dice and using their sum, or drawing a card from a standard deck of 52 playing cards and using the card's value. An ace has a value of 1 and the face cards have a value of 10. Which option has a better chance of obtaining the value of at least 10? Okay, so for the dice. So for the dice, the total number of outcomes, since you're rolling 2 of them, you have 6 options on the first roll, 6 options on the second roll. So you have a total of 36 different outcomes. And how many different ways can you have a 10? At least a 10. So that means at least I could make a 10 and have that. I could also have 11, which is at least 10, and I could have 12, which is at least 10. So how many different ways can I make a 10? Well, I could make a 10 out of a 4 and a 6, or a 6 and a 4. I can make a 10 out of a 5 and a 5, and this is the same thing as 5 and a 5, because 5 is rolled on the first dice and 5 is rolled on the second dice. 4 and 6, 4 is rolled on the first dice, versus the 6 and a 4, 6 is rolled on the first dice. So that's why they're counted, these two are counted individually, is because it's happening in a different way. A 4 is different than a 6 on the first dice. So when we count, and then to make an 11, we could have a 5 on the first dice, a 6 on the second, or we could have a 6 on the first dice and a 5 on the second. And for a 12, we could have a 6 on the first dice and a 6 on the second dice. So there's 1, 2, 3, 4, 5, 6. There's 6 different ways to make at least a 10. So the probability of at least a 10 is going to equal 6 out of 36, which is going to equal 1 out of 36. I mean 1/6. And then we're going to move on to at least a 10. So with the playing cards, the sample space, well, there's 52 cards. And then the probability of at least a 10, well, you have your 10 cards. There's 4 ways to draw a 10 there. You have your jack cards because face cards have a value of a 10, and there's 4 there. Then you have your queens, there's 4 there, and then you have your kings, there's 4 there. Okay, so then the probability of at least a 10 here is going to give me a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 ways out of the 52. And that's going to reduce down to 4 thirteenths. So rolling two dice has a chance of 1/6 of coming up with a value of at least 10, while choosing a card has a 1/13. Nope, it was 4 thirteenths. So then I'm looking for 1/6 again, and it's on the end. Rolling 2 dice has a 1/6 chance of coming up with a value of at least 10, while choosing a card has a 4 thirteenths chance of coming up with a value of 10. So choosing a card gives Ella a higher chance of getting 10 minutes. Yes, because let's check. Is 1 divided by 6? That's 0.116. 166. And what is 4 thirteenths? 0.307. So which one's bigger? Well, drawing your card is greater, because 0.3 is greater than 0.1. Alright, and there is your workbook help.